Today, let's learn about Docker. This tutorial is for anyone wanting to learn how to use Docker in a hobby or professional setting. We will start from the absolute basics and include everything you need to get started, including what Docker is and what problems it solves, how Docker containers differ from virtual machines, how to install Docker, which you can do on Windows, Mac, and Linux, what's the difference between containers and images, pulling, running, and debugging containers, port mapping, environmental variables and arguments, persistence using volumes and bind mounts, building your own Docker images, optimizing images and multi-stage builds, using Docker Compose to orchestrate multiple containers, where we'll put it all together to make a fully functioning application using an NGINX frontend serving HTML, a Python backend using FastAPI, with a MongoDB database, as well as how to publish your Docker images to an image registry like Docker Hub, and some final notes about deploying containers in the cloud. This video is sponsored by Docker. That's right, the company that makes the tool is also sponsoring this video, which is awesome because Docker is a tool that I actually use pretty much every single day. In fact, I've been using Docker for longer than this channel has even existed, so it's great to have their support. Let's get to it. What exactly is Docker, and why would we want to use it? I think it's easier to start with the problems that Docker solves. Have you ever got some code working on your machine, then transferred it to another computer or given it to a coworker and it doesn't work anymore? Or worse, the tests pass on your machine but fail in production? Have you ever burnt an entire day trying to install a program and no matter how closely you follow the docs, it just doesn't seem to work? Have you ever installed an application only to have a seemingly unrelated system upgrade break your application? Have you ever had two applications both individually work fine, but when you try to install both of them, they don't work anymore? These kinds of problems can range from being an annoyance all the way up to crashing your app in production. The underlying cause of all these issues is that your application depends on more than just your source code. You need to make sure that the right versions of all your dependencies are installed, that your operating system has all the necessary packages installed, that any services, config files, users, and permissions are set up correctly, and that none of these hidden dependencies conflict with the hidden dependencies of any other part of your application or the rest of the system. That's where Docker comes in. Docker is software for deploying and running containerized applications. Docker solves all these problems using containers, which are isolated groups of processes. Each container has its own file system that has everything it needs to run, like your app, dependencies, system packages, and so on. So all the issues with conflicting hidden dependencies or system upgrades on the host breaking your code just disappear. Containers are also isolated from each other and the host using kernel isolation features, so containers have a limited ability to affect each other beyond competing for system resources or competing with each other over the network unless you specifically give them extra permissions. You may be wondering, this sounds a lot like using a virtual machine, and you're right. Using a virtual machine with a custom image could provide a lot of the same benefits. However, if you've ever tried running a virtual machine before, you probably noticed that virtual machines tend to be significantly slower than the host. This is because virtual machines emulate, well, entire machines, the kernel, hardware drivers, network stack, everything. And that's a ton of overhead just to run a single application. In contrast, Docker images are made up of normal processes running on the host system. Isolation makes them feel like their own little machines, but they actually use your existing kernel, your existing hardware, your existing network, so you get much closer to native performance and have much more efficient use of system resources than with a virtual machine. So while virtual machine images are typically gigabytes big and take minutes to start, Docker images are usually only megabytes and start in under a second. Next, let's install Docker. If this is your first time using Docker, you probably want to use Docker Desktop, which is available for Windows, Mac, and Linux, and comes with everything you need to use Docker, including both command line and GUI interfaces. If you're more experienced and prefer the command line only, then I'd recommend installing Docker Engine, which comes with the core functionality but no GUI. Docker Desktop does more than just provide a GUI, though. Docker was originally developed for Linux, and most Docker containers are for Linux. So Docker Desktop uses a hypervisor layer to run a lightweight Linux distro, which is what allows you to be able to run Linux containers even when you're on Windows or Mac. I'll show you what I do to install Docker, but keep in mind that setup instructions change over time, so always refer to Docker's official installation instructions for how to install for your system. In particular, make sure you're running an operating system version that is specifically listed as supported. I'm on Linux using a fresh install of Ubuntu 22.04. As always, make sure your system is up to date before installing anything. Next, I'll set up Docker's package repository following the instructions at this link. All you need to do is copy and paste this code into your terminal. Then I'll download and finally apt install the .deb file. It looks like we got an error, but according to the docs, this is expected and we can just ignore it. And that's it. Let's start up Docker Desktop in order to start the Docker daemon, which is what manages containers under the hood. Review and accept the service agreement. And I'll go ahead and continue without signing in for now. Skip the survey, and we're in. You can set it to run on startup in the settings if you want. We can now run Docker commands, so let's start by running hello world. We did that with docker run hello world, and as you can see, it pulled the latest hello world image and ran it. If we run hello world again, it doesn't download the image again since we already have it downloaded. If you wanted to download the latest image or pull a specific image without running it, you can use docker pull. In this case, it just confirms that indeed we have the latest image that we downloaded just a few seconds ago. And a quick security note, by default, Docker runs with root privileges, because it needs to be able to do things like bind to privileged ports, mount file systems, and modify network settings. It's possible to run Docker without root, but that's beyond the scope of this video. Now that we can run Docker commands, we should get some of the basic concepts down. The first one is the difference between Docker containers versus images. Take a look at our Containers tab, where we have two separate containers that both have an image of Hello World. Whereas in our Images tab, we only have one image, Hello World. The relationship is that images are templates for containers. Images specify the contents of the file system, what applications are installed, users, environmental variables, and the default command that will run when you start a container. You can think of an image as a recipe for running an application. Containers, on the other hand, are the actual groups of processes that are launched that follow the instructions the image specified. Every time I use Docker to run an image, it creates a new container based off that image. That means I can have many containers all based off the same image, even running at the same time. You can see your images and containers in their respective tabs, or Docker image ls will show us images, and Docker ps will show us running containers. Our hello world's already exited, so we see nothing. If we want to see them, then we use a -a flag to include all containers, including stopped ones. Let's try running something with a little more substance than hello world. How about an NGINX web server? NGINX is publicly available on Docker Hub, which is the default image registry that Docker uses if you don't specify. So we can use docker pull nginx, or in our case, docker run nginx. And that downloads and runs the latest version, in this case, 1.27.0. It looks like it downloaded and started up fine. This output here is the logs for the container. We can see it's still running in the GUI, but when we visit localhost, we don't see anything. That's because by default, containers are isolated from the host network. In order to interact with the NGINX server, we need to publish the port it's listening on so our host can see it. We do that using the -p flag. Let's stop it and try again. Now when we go to localhost, we see the default NGINX page. In this case, we wanted to publish the container's port 80 to our own port 80, but you can remap ports however you like. If we wanted the NGINX page to be available on port 5000, we could run the same command with 5000 instead of 80. Now the containers port 80 is available on our port 5000. I've also been running this container in the foreground so far, and I've been stopping it using Control-C. If you want to run the container in the background, you can slap on a -D for detach. Now my terminal stays free. This string that it printed out is the container ID, which I can use to interact with the container while it's running, or to help me locate it in the GUI. We can see part of that ID here with Docker PS. For most commands that need a reference to a container, you can refer to it either by the container ID or by its name. You can specify a name when you launch the container using --name, otherwise one will be randomly generated. That's what we see here, a randomly generated name. If I wanted to see the logs that were being printed out before, I could use docker logs and then paste in either the name or the container ID. Or of course, I can go to Docker Desktop, find the container in the list, open it up, and look at the logs in the GUI. You can also stop containers in the GUI as well, or by using docker stop. We've also started to accumulate a bunch of containers here. These will not be deleted unless you delete them, which can be done in the GUI or with docker container prune. This will remove all stopped containers. Or you can tell Docker to automatically delete a container when it stops by using the --rm flag in the run command. Next, let's talk about tags. You may have noticed that in our docker run command, we just said NGINX. But what version of NGINX are we running here? If you don't specify, you just get the latest version, or the latest version you already have downloaded. We can pick a specific version by adding a colon and a tag. NGINX 127 will give me the NGINX image that's tagged with the label 1.27. But be warned, Docker tags are like symbolic links. NGINX 127 points to some image. Currently, it's an image running Debian Bookworm with NGINX 1.27.0. But when NGINX 1.27.1 gets released, they'll most likely update the 127 tag to point to a new image that's running NGINX 1.27.1. To mitigate that risk, you can use a more specific tag like NGINX 127.0-bookworm that's very unlikely to be updated to a new image, or you can pin the image using its digest, which uses the SHA-256 hash function. The digest was printed out the initial time we pulled the image, or we can find it using docker image ls-digests. Or it's also displayed on Docker Hub. You can go to the tags list and then search for the tag that you're interested in. Look for it in the list here. In this case, we want 127.0 bookworm. And here's that same digest. Then whenever you specify the image, put an @ with the digest at the end. If you provide a digest, you can leave the tag there for humans, but it's ignored. Pinning by digest is the only way to have high confidence that no changes are introduced into your container's environments unless you specifically asked for them. For a production application, I highly recommend pinning by digest, not by version. This is effectively the same advice that I give for Git tags and for Python package versions. Tags are great for humans, but they don't provide the kind of stability that hashes do. But if you're just playing around or using private images, then tags are fine. Moving on, let's talk about environmental variables and arguments. Just like normal programs, containers can be run with environmental variables and arguments passed at runtime. Just to demonstrate, let's run Python and pass it some environmental variables. You pass environmental variables with -e flags. And you pass the command and args to run just after the image. Here, we're still going to run the default Python command, and we pass it the -c that allows us to give an inline script to run that prints out the environment. The output shows our ABC123 and our DEF456. But I don't know if you noticed, because the wait time was cut out in the video, but this Python image is over a gigabyte big. Time to talk about Slim and Alpine images. In production and testing settings, image size matters a lot. Python, like many other popular images, provides tags that come with various different environments with various different things pre-installed. The default Python image is currently based on a fully featured Debian install. In contrast, any of the tags that have Slim in them are based off a much more bare-bones version of Debian. Pulling that image, we see it's nearly 10 times smaller than the non-slim version. If that's still too big, keep an eye out for tags that have Alpine in them. Alpine refers to Alpine Linux, which is a lightweight Linux distro focused on minimalism. Pulling the Alpine image, we see it comes in at only 55 megabytes, around half the size of the slim version and 20 times smaller than the main version. I recommend using either the slim or Alpine images if they're available. However, while slim is usually an easy win over the non-slim version, choosing between slim and Alpine is not as obvious. Alpine Linux is significantly different than Debian Linux. Alpine uses musl libc instead of glibc, it doesn't come with bash, and it uses the APK package manager instead of apt. So there's a learning curve and also a risk of subtly different behavior than you may be used to on a Debian-based distro. Next up, debugging containers. Let's say we have a container running, and something's not quite working the way we want to. Yes, we can inspect the logs, but sometimes you just need a shell to poke around. The two main ways of doing this are, number one, using the GUI. Clicking this exec tab gives you a root terminal where you can play around. Alternatively, you can use Docker exec at the command line, which allows you to execute a process on an already running container. The -IT stand for interactive and TTY. Interactive keeps standard in open, allowing you to interact with the process, and TTY allows terminal features like command history and autocomplete to work properly. The specifics aren't that important, just remember if you want an interactive session like a shell or a REPL with Docker run or Docker exec, use -IT. Of course, now we're root inside the container, so we can debug to our heart's content. Moving on, we need to talk about persistent storage. From everything we've seen so far, every time we run a Docker container, we start fresh with a pristine container generated from the same image that starts with the same file system every time. Any files written from the previous runs are gone. We can demonstrate this with a simple Python script. All it does is open a file, write to it, and then print out the contents of the file. But every time we run it, we still just see one copy of ran because it's starting clean every time. But many applications, like databases, have data that they want to persist across runs, even to persist across image changes, like upgrading the database version. We can achieve that using a mount. You can add a mount to your container using -v, which stands for volume, or using the more verbose --mount syntax. This time, the /data directory is populated by a volume that lives beyond the lifecycle of the container. So each time we run the script, we see the previously saved data. Currently in Docker, there are three kinds of mounts: volumes, bind mounts, and tempfs mounts. Volumes and bind mounts are used for persistence, whereas tempfs mounts aren't persisted and are beyond the scope of this video. Volumes are newer, more fully featured, and are completely managed by the Docker daemon, whereas bind mounts mount a local file or directory from the host into the container. The syntax of using a volume versus bind mount is nearly identical. They both use the -v flag. It just depends on whether you give it a name like mydata, or a relative or absolute path like /mydata or ./mydata. If you give it a path, then Docker will mount the source path into the target path as a bind mount. If you give it a name, then Docker will mount a named volume into the target path. Let's try creating a mydata directory and passing ./mydata to the -v. It seems like this version also works and persists our data. The only apparent difference right now is that we can directly see and manipulate the contents of the mydata directory, whereas the mydata volume is stored in some location managed by Docker that we don't really know about. So which one should you use? It really depends on why you want to share the data with a container in the first place. When you're developing code on your local machine, bind mounts tend to be what you want because their main benefit is that they're simply mapping a file or directory on the host into the container. You can see all the files right there, inspect them in your IDE or with other programs, and change them as you please. This can be really useful to quickly modify an image to your liking by sharing a config file or build artifacts between the container and the host. It allows you to quickly iterate without going through the process of building your own image and rebuilding it every time you make a change. Watch out though, mounting a host directory means you're giving the container direct access to that directory, meaning a container can modify or delete files or change permissions of files on the host. This risk can be mitigated by setting the mount to be read-only, which is what this :RO at the end does. But sometimes containers just need write access. A common annoyance is when a container owns the directory to root within the container because it's a sensitive config file, which then makes your current user unable to view or modify the files until you sudo chown them back. Volumes, on the other hand, tend to be much more appropriate in a production setting because of the additional features they provide that are useful in cloud environments. Since volumes are managed by the Docker daemon and not the host file system, volumes can be easily shared across multiple containers, even containers running on different hosts, or with the underlying data stored on a remote host or cloud provider, such as in an Amazon Elastic file system, an NFS share, or an SSH file system. Volumes also abstract away the file system of the host, which removes the risks associated with giving a container access to files on the host. But the flip side of that is that you can't conveniently view or modify the contents of a volume from the host. I mean, if you use a local volume, the files are all there, it's just not convenient. The primary way you're meant to interact with a volume is through containers, not directly from the host. But for many use cases, you might not care to actually see those files. Unlike a config file that I might want to go back to, reference, and iterate on, the underlying storage for a database is typically not in a human-readable format anyway, so providing a directory in my project folder for a database to store all its junk is more of a nuisance than anything. In that case, a volume would be more convenient than a bind mount, even in a development setting. So use volumes, use bind mounts, don't let anyone tell you you're doing it wrong, especially when you're learning, just do what works for you. So far we've seen how to use existing Docker images, but we only customized them through environmental variables, arguments, and mounting files and directories. If you ever want to customize beyond that, Docker makes it super simple to build your own images. I went ahead and installed all my dev tools. Let's open up a new project folder in VS Code. I always recommend creating a project folder when you're creating Docker images to stay organized. Let's start by creating an image with an NGINX server that serves custom HTML instead of the default. That's a frontend service, so let's make a frontend folder and a single file named Dockerfile. Make sure to install the official Docker extension to get autocomplete and syntax highlighting. Although Dockerfiles completely specify the file system, we don't have to start from scratch. You can, and usually do, use another image as a starting point by using the from keyword. Let's base our image on NGINX 1.27.0. At this point, we can already build our image using the docker build command. Take note that the -t flag specifies the name and optionally a tag. And don't leave off that dot at the end. The dot specifies the build context, which tells Docker where it's allowed to look for files, in this case, the current directory. By default, Docker uses the Docker file at the root of the build context, or you can specify the path to a Docker file with -f. Anyway, we see that Docker created our image, and now it's listed in our Docker desktop. We could run it too, but right now it's just a copy of NGINX, which we can see by comparing the hashes, so let's customize it. Let's create a static folder for our HTML and put a minimal index.html that maintains a to-do list. Feel free to pause to check out what the JavaScript is doing. It's pretty simple. We just have a single function to add an item to the list that also creates a button to delete that item. Starting from an NGINX image, all we want to do is copy this code from the static file into the directory that NGINX expects its HTML. We do exactly that with the copy command. The sources of a copy command are relative to the build context, in this case the frontend directory, whereas the destination of the copy is a path inside the image's file system. Let's go ahead and build and run our image. And voila, we see the most beautiful website known to man. If we exec into the container and navigate to /user share NGINX HTML, there we see the contents of our static folder. The NGINX image left this 500 error page there, so let's delete that using a run command before copying everything over. Run just runs a command inside the image. Then let's build and run again. And there we go, we have a nice and clean directory with just our index file. I want to point out how fast the build process was. How is it that we're specifying an entire file system, but it takes basically no time to build? The answer is due to a fundamental concept in Docker: layers. Layers are like image diffs. At build time, the Dockerfile is run in order, and each command that you run in your Dockerfile creates a new layer based off the previous one. Because layers act like diffs, a small change like deleting a directory or copying a folder results in a small diff. Layers are also immutable, so even an operation like a delete creates a new layer. It doesn't modify an existing one. Importantly, Docker doesn't just store the final image, it stores all the individual layers, which makes it possible to reuse existing layers. Since we already downloaded the NGINX image, Docker already has all its layers cached for immediate use and just needs to apply 2 tiny diffs to create our final image. That's what we're seeing here. Docker Desktop lets you inspect the layers in an image and the commands that created them, which is a great way to learn about Dockerfiles. At build time, Docker attempts to use cached layers wherever possible. Docker will check the current command against the last time you built and reuse the result unless the cache was invalidated. Different commands have different caching rules, but the main ones to keep in mind are: number 1, changing a command invalidates the cache for the current and all later commands. So if I change this 127.0 to 127.1, it will have to download all the new layers from 127.1 that weren't in 127.0, then it will have to rerun the run and copy regardless of whether anything else changed. But if I changed the run command, it would only rerun the run and copy. If I changed the copy, it would only rerun the copy. And rule number 2, most commands are cached by default, even if they aren't pure functions. This run command is pure. The resulting image relative to the previous one should be the same every time regardless of when you run it. But in general, a run command can do almost anything. You could apt-get install some package today, and tomorrow the same command might download a different binary. But Docker will cache and reuse the result from today. If you want, you can force Docker to not use the cache with --no cache in your build command. But don't worry, the copy command additionally uses file metadata to invalidate the cache, so if your source contents change, it will at least invalidate copy commands, even if your Docker file doesn't change. We'll see some caching tricks to speed up builds later on. And one final security warning about layers before we move on. To reiterate, a run command that deletes something does not modify the previous layer. It creates a new layer on top of it. That means it's not safe to put any sensitive information inside a Docker image, even if you delete that information in a later command. Layers are like your Git history. Creating a new commit with a certain file deleted will not stop a malicious user from pulling that data out from the history. Now that we have a front end working, let's create a simple Python backend to store our to-do list so that it can persist across refreshes. Go ahead and create a backend directory with source and my site directories within it with a main.py file. Also remember to create and activate a new virtual environment. Go ahead and pip install FastAPI, and then use pip freeze to create your requirements.txt file. Again, in a production setting, I recommend pinning not just versions, but hashes as well, but that's out of the scope of this video, so we'll just pin the versions. In our main.py, let's start with some imports and creating the FastAPI object. Next, we create 2 Pydantic models for our to-do items. An item will have an ID and some content, but creating an item will just require the user to give us the content. We'll store the to-dos as a global in-memory list and just use a global counter to generate IDs. Then we'll have 3 endpoints, one to create to-do items, one to list all the to-do items, and one to delete a to-do item by its ID. Feel free to pause here if you'd like to check out the implementation of the endpoints, but they should be pretty straightforward. Next, let's create a Dockerfile at the root of our backend directory. We'll base our image on Python 3.12 Slim. This workdir command sets the working directory inside the image. It's common to store your Python project in an app directory like this. Then let's copy over our requirements.txt and run pip install to install our requirements. After that, we copy over the rest of our source. We could have copied the requirements and source in a single copy command, but splitting them is actually intentional. Remember, if nothing changed, then Docker will cache previous commands, including this run. Requirements files change far less frequently than source files, so I copy and install the requirements first. Then, as long as no requirements change, a change in just a source file will not require rerunning the pip install command, which is the slowest part of the build. We also give pip the no cachedir option, because the cachedir would be inside the image, which would be pointless. Next, we use the expose command, which I think is quite confusing. This is not a way to automatically expose a port to the host. Whether you expose in your Dockerfile or not, you will still have to use the -p flag when you run it in order to publish the port to the host. In older versions of Docker, expose actually did something meaningful, but the modern purpose is that the expose command is basically just documentation for the reader. But I still use it because documentation is good. Finally, we have the command command, which specifies the default command that will be used if none is supplied when you run the container. This command will be executed using /bin/sh, but there's also an entry point command if you want to specify a different executable. Command and entry point also allow you to specify either a string or a list of strings like we do here. I always recommend using the list of strings approach. Great, let's build it and run it, remembering to publish port 8000. Looks like it started up just fine. Let's open it in the browser. Open up /docs and we can see our FastAPI Swagger docs with our 3 endpoints. Next, I've updated the front end to actually call the back end. I've just hard-coded the URL here, and I'm using the built-in JavaScript fetch. We list our to-dos using the get endpoint. We add an item using the post endpoint, and we delete an item using the delete endpoint. Let's rebuild and run them both. Let's test it out. And as per always, we forgot to add the CORS middleware, so the browser is blocking our requests. CORS is beyond the scope of this video, but the short answer is that we access the website from localhost on port 80, but the JavaScript is calling out to localhost on port 8000. For security purposes, those are treated as 2 completely different websites, so the browser treats that as malicious behavior and blocks it unless the response specifically indicates that it's okay. Back in our main file, we just need to import and add this CORS middleware. Let's rebuild and run it again. And now our backend and frontend are both up and running and talking to each other. Just to show you that it's working, let's add some items to the list. And see that even after a refresh, we still have our items in the list because that's now persisted by the backend. Well, as long as we don't shut the backend down. At this point, I want to show a neat trick with Dockerfiles that helps both with security and can drastically lower the overall image size. I'm talking about multistage builds. Take a look at this Dockerfile again. The problem here is that the final image includes things that were only needed during the build process and are not actually needed in production. Our example is pretty minimal, so there's basically just this requirements.txt that isn't needed at runtime. But in a general application, your build dependencies and runtime dependencies can deviate significantly. They can include things like heavy build systems, a C compiler, and so on, and the build process itself can generate many unwanted files like caches and logs. This can also be a security risk because having build tools available on a production machine leaves a much greater attack surface. Introducing multistage builds. What we can do is separate the commands used for building versus running the application into separate stages. In our build stage, the goal is to produce all the wheels we need to install so we can just copy them into our run stage. Then all the run stage needs to do is install those pre-built wheels and run. In order to make this work, we'll need to make our project an installable package first, which I recommend doing anyway. So let's add a pyproject.toml file to make our code installable. Here's a pretty minimal one using setup tools. We just set our project name, Python version, our project version, and then any hard dependencies, and then we specify where to find our packages. I also added this empty init.py. That's all we needed to do in order to make our package installable, so let's get back to the Docker file. This time we copy over our infrequently changing project files, but instead of pip installing into our environment, we use pip wheel to create pre-built installable wheels, which are like glorified zip files. Then we copy over our source and build a wheel for that as well. We define more stages by using more of these from commands, and since we have more than one, we should give them both names. In the runner, we use this copy command with this special -- from to tell Docker the source location is not from our build context, but rather from the previous builder stage. We copy all the wheels over, install them, then delete the wheels. I snuck in another optimizing trick here. Notice how we're using a single run command with 2 commands in it. By grouping commands together, we can decrease the number of layers and potentially squash creates and deletes that cancel out, although that doesn't apply in this case since our wheels were not generated in this run command. Now, no matter how complex the build process was, the runner image has no build dependencies. We started fresh and directly installed the production wheels. Time to rebuild. In this case, Docker automatically selected the runner as our final target, but you can have many stages in a multi-stage build, like a builder, dev, test, and prod runners. But if you have a specific one you're looking to build, then you can use -- target and specify the stage name. You could also use multiple Dockerfiles instead. Just do what works for you. As you may have noticed by me fumbling around, it can get pretty cumbersome to manually launch everything when you have multiple containers. They may contain different ports they need to publish, have environmental variables, volumes, and so on. That's because Dockerfiles are for individual components, like our frontend, our backend, but our application isn't just a single component. Our application is a composition of components all orchestrated in a particular way. We have a frontend, backend, maybe a database, a load balancer, a Redis cache, a task queue, and so on. For these compositions of components, we use a higher level tool called Docker Compose. Create a Docker Compose.yaml file at the project root. We specify each of our components as a separate key under the top level services key. For the backend, let's give the image and container a name. And since we're building the image, we need to add build info. We want Docker to build the backend as if the backend directory was the root in the build process, so we set the context to be the backend folder. By default, it'll use the Dockerfile named Dockerfile, but I always like to specify it by name since you might have more than one. The backend is a multi-stage build, so I also like to be explicit about the stage we want as the final result, so we set the target to be the runner stage. Then we can specify the ports that we want to publish, just like we're using the -p flag in Docker run. Unlike the expose command in the Dockerfile, this ports configuration will actually map ports between container and host. Add another top-level key for the front end, which is similar. We have an image and container name, and we specify a build. The front end is not multi-stage, so we don't need to specify a target, and we expose port 80. In order to avoid accidentally pulling some random person's image from Docker Hub that might have the same name, you can either set the pull policy to never, or you can change the image to point to a repository you own. For now, let's just set the pull policy to never. Next, let's use Docker Compose to build all the images. Now that all the images are built, we can start everything all at once using one command, Docker Compose up. If you've never seen this before, it's pretty cool. One command and our whole stack is up and running. You can see the logs from both of the containers here. You can use the -d flag just like you can with Docker run in order to do everything in the background. We can also see everything nicely grouped together in the Docker desktop GUI. You can shut everything down by clicking this button, or with Control-C at the terminal, or with Docker Compose down. Docker Compose down actually deletes the containers. So if you just wanted to stop them, you could have used Docker Compose stop. And Docker Compose start to start them back up again. Though I usually just use up and down. I hope you can see this is way more convenient than starting and stopping everything manually. And using Compose also creates an isolated network just for these containers. as opposed to putting everything in a global default network or having to manually manage networks yourself, which I didn't even talk about. Letting Compose do it is just easier. Now that we have Docker Compose at our disposal, let's see how to add a database to our stack so that when we shut down our server and start it back up again, we don't lose all of our data. In our Compose file, add a new service for MongoDB. This is another public image. Let's grab version 7.0.12, which is the current latest release. Set a container name. We have nothing to build. And for this one, we actually don't need to specify any ports to publish because we don't need to access the database from our host. We only need to access the database from our backend. Compose creates a network for the services, so by default, all the containers in this Compose file can talk to each other. Additionally, it's set up so that they can refer to each other by their service names. So when it comes time to tell our backend the connection string for the database, we can just use MongoDB for the host name. Since we need to persist our database data, let's use a volume, which we can specify in the Compose file. Create a top-level key for volumes, and since the default volume options are fine, all we need to do is specify the name of our volume we want to create. Let's call it MongoDB data. Then in our MongoDB service, we specify that MongoDB needs to mount that volume at /data/db, which is where MongoDB expects it. Lastly, our MongoDB needs a username and password, which the image expects from environmental variables. You can pass environmental variables like this, but do not do this with sensitive data like passwords. Dockerfiles and Compose files are meant to be tracked in your Git repository. Therefore, they should not contain any secret data. Instead, you can pass environmental variables using an env file like this. Create a folder for the MongoDB service, and in there, create a file named .env. Take the environmental variables and put them in this .env file. Then in your Compose file, use the env file key, specifying the path to your .env file. Immediately afterwards, you should create a git ignore and add .env to your git ignore so you don't accidentally commit any env files. There are still security considerations around storing secrets in environmental variables at all, particularly if you're running untrusted or malicious code on the same machine, if you expect your server to be compromised, or if you need to segregate who at your company has access to production hosts versus who has access to the secrets. Those kinds of concerns are beyond the scope of this video, but if you're worried about that, then what you need to look into is called a secrets manager, like AWS Secrets Manager or HashiCorp Vault. Docker also has a built-in secrets manager, but in production this requires the use of Docker Swarm mode. Moving on, this is enough to run a database, but we need our backend to actually connect to it. For that, we'll use the motor library, which we need to add to our pyproject.toml and requirements files. I just installed it in my local environment and then used pip freeze to update the requirements. Then in the code, I made a few simple changes. Firstly, we'll grab the connection string from an environmental variable, create the motor client, and get the to-dos collection. Then we update our to-do models. Our to-do item now uses UUIDs for the ID field, and we use this _ID alias because _ID is what MongoDB uses as a primary key. Then we had to update the 3 endpoints to actually use MongoDB. The changes are pretty straightforward. We just swap out our list operations for MongoDB insert, find, and delete operations. We also create a .env for the backend to pass that connection string. This first MongoDB is the protocol, then root and example is our username and password, and this second MongoDB is the hostname of our MongoDB container. Just to reiterate, because we're using Docker Compose and the MongoDB service was named MongoDB in the Compose file, that's what allows us to use the hostname MongoDB here and have it be directed to the other container. The port 27017 is MongoDB's default port that it listens on. Then we go ahead and add that .env to our Compose file as well. Lastly, we have one tiny change we need to make in the front end because we changed to using _ID instead of ID. Add in that underscore so that deletes work properly, and we should be set. We're ready to rebuild. And just like that, with one command, Docker Compose up, we now have a front-end, back-end, and persistent storage in a database, all in one command. Let's check it's all up and running on localhost again. Refresh. Let's add some items, ABC, sleep, and code. Then let's go back to our terminal and Docker compose down to kill everything. And Docker compose up to start it all again. And refresh the page, it's all still there. We can delete items and add new ones, just like nothing happened. And the best part is, a collaborator can clone this project, run docker build, docker compose up, and everything will work exactly the same way that it works on my machine. And pro tip, during development, I recommend using Mongo Express to easily explore your database. Just add it as another service in your compose file. It exposes a web interface on port 8081, and create a Mongo Express folder with a .env so we can pass environmental variables to it. It needs the connection string to the underlying database, and then a username and password for its own interface. Docker compose down, and Docker compose up. Then visit localhost on 8081, put in root and example, which were from the config. And now we've got a convenient way to explore our database. Here's our to-do list database with the to-dos collection, and we can see our 3 to-do items, sleep, code, and continue. Being able to actually view your database in a development setting makes debugging a lot easier because you can just go in, see the actual data, and even edit it right here. Back to the compose file, you may wonder about the order that containers start up in. In particular, some containers depend on others being available. For example, when our backend starts up, it immediately tries to connect to the database. But what if the database container hasn't started yet? Docker has this depends on key where you can specify for each service which other services need to be started first. Then Docker will make sure that the containers start in an order where nothing is started before its dependencies. This can be convenient in a pinch, but I don't really recommend this option. I'm much more in favor of writing your code in a way that works regardless of the startup order, often by having services use timeouts, retries, or pinging your dependencies to see if they're ready before continuing with normal startup. In this compose file, none of the services actually require the others to be started first because they all internally have timeouts or retries built in. But you may find it useful anyway. While Docker is incredibly useful even just for local development, at some point you may want to share the images that you create, either to a public repository for everyone to benefit from, or to a private repo, probably just to use within your company. This is done through what's called an image registry, which is a service that hosts Docker images. The default and most popular image registry is Docker Hub. The process for publishing is actually pretty simple. Make sure you have an account with the registry you're using and create a repository for your project. I just created this public demo script repo under my username. Then tag your image, log into your registry, and push. You can either put the image including tag in your Docker Compose, or you can tag the image manually using Docker tag. Even though I don't have to, I like to specify docker.io out front just to remind myself that pushing this image goes to Docker Hub. If you use another registry, like one hosted by your cloud provider, change that docker.io to your registry. Keep in mind that you can tag a single image with as many tags as you like. This is how a lot of really popular images work, like NGINX. Currently, NGINX, NGINX 127, NGINX 127.0, and NGINX 127.0 Bookworm all point to the same image. There's no hierarchical structure to tags. The NGINX team literally just tagged the same image with a bunch of different tags for your convenience. You can do the same thing with your tags, although personally I prefer to tag every image with a single tag that specifies its full version and never change what image a tag points to. I already built this image, and note that Docker Compose build will tag the image with whatever you put here. Then we need to log in. If you're on Linux, there are a few hoops you need to jump through because Docker uses the password manager to store your credentials, so you need to set that up first. First, you need a GPG key, which you can generate with GPG generate key. Then copy this and do pass init and paste that in. Then you can log in either from the CLI using Docker login or directly in Docker desktop. Then use Docker push, specifying the image and tag you want to push, or use -- all tags to push all tags associated with an image. Looks like the upload succeeded. Let's go back to our repository and refresh. And there it is. Our first ever Docker image is available to the world. Run it if you dare. And lastly, let's talk about deployment, which is a whole beast of its own. You don't actually ever need to deploy your containers if you don't want to. It's perfectly fine to use Docker as a local development tool only, or as an easy way to install and run specific versions of specific tools you need. But suppose you do actually want to deploy your containers. You can download Docker onto a server you control and manually pull and run your images, but that's not the typical way of doing it. When it comes to deployment, the conversation very quickly turns to which paid cloud service provider offers the most convenient and affordable container running product for your use case. There's no one right answer here, and there are hundreds to choose from, so you're just going to have to do some extra research. Anyway, that's all I've got. Once again, huge thanks to Docker, both for making Docker, as well as for sponsoring this video. Thanks to my patrons and donors, and as always, slap that like button an odd number of times. Don't forget to subscribe and comment, and I'll see you in the next one.